Hello. In this video, we work with problems based on reaction kinetics. So we introduced reaction kinetics in class. Now we are just focusing on problems that you have to work on so that you are ready for class activities. So we'll talk about our focus will be on the first order rate law, and then later on we'll talk about what we are actually discussing. So as a reminder, for a reaction where we have a reactant from A to give us product, we know that integrated first order rate law is given by natural log A T is equal to minus K T plus natural log A naught. So AT is the concentration after time T, while A naught is the initial concentration. So this is at time T is equal to 0, before a chemical reaction has started. So this is the integrated rate law of the first order reaction. So I'll just say first order reaction. That's the law that we have for first order reaction. So let's take note of this. How do we use this law in a question or in a problem? So let's go talk about what we are discussing, and then we'll go on to see how we use that integrated rate law. So first we'll talk about the integrated rate laws, especially the first order problem, and we'll talk about half-life, and then we'll go on and discuss the Arrhenius equation and the problems that it deals with. So let's go back to that first law. In this case, our A is SO2Cl2. So this is the same integrated rate law, but here we have A, here we also have A. So we can just say this is A naught, this is AT. So instead of AT, we have a real concentration of a substance here, and this is the initial concentration of a substance. So K is the rate constant. As we already know, T is the time that has lapsed, the time that the reaction has taken to occur. So let us look at this equation, the first order equation. If the initial concentration of SO2Cl2 is 0.0225 molar. What is the concentration after 865 seconds? So that's the first problem that we are going to solve. The second problem, if the initial concentration of SO2Cl2 is 0.0225 molar, how long will it take to reach a concentration of 0.0025 molar? So that's the second problem that we are going to solve using the first order rate law. So let's go on and work on these problems. So we see the integrated rate law given there. What we want to find is the concentration after 865 seconds. So let's look at this. What are we given? So I'll say given. We are given the initial concentration. This is what we know. So this initial concentration here is, so I'll say this is SO2Cl2 naught is 0.0225 molar. So what else are we given? We are given time. So we are given time, which is T. This one is equal to 865 seconds. What else do we know? We know K. So the K is given 2.90 times 10 to the power -4. Since if it's first order, it should be per second. It should not just be second. It should be to the power -1. So that is our K. So we are given three things. We are given this one, and that. So we know that our equation is natural log SO2Cl2 T is equal to minus KT plus natural log SO2Cl2 naught. Now what we need to do is just to substitute. Instead of K, we put the number 2.90 times 10 to the power -4 per second. Then we put our time for T, which is 865 seconds. Then plus the natural log of the initial concentration, 0.0225. So once we do that, we just need to get the numbers. So that one, 2.90 times 865. So this one gives us 0.0251, because these seconds here are going to cancel, plus, so natural log 0.0225 plus this one will be minus 3.79. So the answer for this one will be minus 4.04. So we are saying that the natural log of SO2 Cl2 at time t is equal to negative 4.04. Now, the concentration of SO2 Cl2 at time t is given by the e to the power 4.04. That is the natural log of that. So e to the power 4.04. So for this one, the concentration will be 0.0176 molar. So you need to know how to use your calculator, and also you need to know that you need to get rid of the natural log. To get rid of the natural log, you bring out your concentration here, but the answer here should be raised, should be the power of this e, because that's how we move from a natural log to natural log. So we are saying this is the concentration after time t. Now let's go on to solve the second problem. If the initial concentration of SO2 Cl2 is 0.0225 molar, how long will it take to reach a concentration of 0.0025 molar? So for this problem, we look at what we are given. So we are given SO2 Cl2 T, which is this one here, which is 0.0025 molar. We are also given naught, which is 0.0225 molar. What do we know? We also know T, we also know that is K, 2.90 times 10 to the power negative 4. So I said this one should be S to the power negative 1. So I'm changing this one, S to the power negative 1. What do we want to determine? We want to determine T. That's what we want. We want to find T. Now, as previously, what we want to do is to isolate the t. I will do it in such a way that it's easy to understand. So I'll start with our formula. Natural log SO2 Cl2 T is equal to minus K T plus natural log SO2 Cl2 naught. Now we are saying that we have all these other things. So here natural log of 0.0025, we know that this SO2 Cl2T is 0.0025 molar. Is equal to minus 2.90 times 10 to the power negative 4 S minus times T plus natural log 0.0225. That is the initial concentration. So we can change the natural logs to just be numbers 0025. So this one is minus 5.991 is equal to minus 2.90 times 10 negative 4 S minus 1 T plus natural log 0.0225. So this one is minus 3.794. So when this minus goes this side, it becomes plus. So this one becomes minus 5.991 plus 3.794 is equal to minus 2.90 times 10 to the power negative 4 times T. So if I add the 2 there, minus 5.991 plus 3.794. So this one becomes minus 2.197 is equal to minus 2.90 times 10 to the power negative 4 S and T. Now you want T to be subject. In that case, you need to divide both sides by minus 2.90 times 10 to the power negative 4 S. You do the same thing this other side. Minus 2.90 times 10 to the power negative 4 S. So this cancels with that. When we divide the 2, the negative here will cancel with the negative. So if you are using calculator, please use parentheses. So I'll just say 2.197 divided by open parentheses 2 2.9. Second function E -4. Close parentheses. So the answer here is 7, 5, 7, 6 seconds. So I'll just say that is the time it takes the concentration to reach 0.0025. So that's how we solve this problem. When you are given the initial concentration and the concentration at time t, what you want is to make t subject of formula. So this is how we solve these first order reaction equations and problems. Now let's move on to something else. Let's go on and discuss half-lives. So by definition, a half-life is just time. It is time taken for concentration to fall to 1/2 of its initial value. So if we start with the concentration of 1, the time the concentration reaches 0.5, that is half-life. If we start with the concentration of 100, or if we start with 100% of the concentration, the time the concentration reaches 50%, that time is half-life. Now, I'm not going to derive the half-lives here. I'll just tell you the half-life expressions for a first order reaction and a second order reaction. So just you just need to know these half-lives. So for the first order reaction, the half-life, which is given as t half, is equal to the natural log of 2 divided by the rate constant. The natural log of 2 becomes 0.693. So this one is 0.693 divided by k. That is half-life of a first order reaction. So based on this, the half-life of a first order reaction does not depend on initial concentration. So it just depends only on rate constant. That's what it depends on. What about half-life for second order reaction? So for this reaction, the half-life is given by 1 over K, then initial concentration. This tells us that half-life of a second order reaction depends on initial concentration. So let us take note of these two half-lives. If I ask you, tell me the half-life of second order, this is the half-life of second order. Tell me the half-life of first order reaction, this is the half-life of first order reaction. So let us see what problems we can solve using these half-lives. But before that, let's suppose that you start with 1, a concentration of 1 molar. You can reach multiple half-lives, and the graph here shows you the multiple half-lives. So the first half-life, if you start with 1, the first half-life will be given by 1 divided by 2, which is 50. So this will be your first half-life. The second half-life will be given by, 1 divided by 2 is 0.5. The second half-life will be given by 0.5 divided by 2, which is 0.25. You can see here. The third half-life will be given by 0.25 divided by 2, which is 0.125 here. So from 1 to 0.125, we have 3 half-lives. So first half-life, second half-life, third half-life. So let us take note that usually we have multiple half-lives. We don't just have a single half-life. So we have multiple half-life, and they give us this type of decay, exponential decay graph. So that is half-life graph. So I'll just say exponential decay graph. All right, so let us solve some half-life problems. This one will deal with I'll just say this one deals with multiple half-lives. The half-lives are used to determine the radioactivity of iodine 131. If we start with 1800 iodine 131 isotopes, how many half-lives will it take to remain with 215 iodine 131 isotopes? So let us take note, radioactive decay is always first order reaction. So it can not be second order reaction. It is always first order reaction. So if we are talking about the half-life should be that for the first order reaction. But this is multiple half-life. So the solution is really simple. The best way is to move step by step. The best way is to move step by step. So you say, you know what? At first, I have 1800. So to get to the first half-life, I'll have to divide this by 2 to give me 900. So this is your first half-life. Now, to move to a new half-life, I'll need to divide the 900 divided by 2, which gives me 450. So this is my second half-life. Now, to get, but this is not yet 215, which means I need another half-life. So 450 divided by 2. So I want to get a third half-life, which gives me 225. This is third half-life. Now, the third half-life has 10 more to this 15. So this is 215, this is 225. But if we get to the fourth half-life, it will be way, way, way less than 215. So we can say that, you know what, 225 is really close to 215. Therefore, we need 3 half-lives to get to 215. So we need 3 half-lives to get to 215 iodine 131 isotopes. So that's how we determine the half-lives. Based on multiple half-lives. Let us look at another half-life problem. So the same reaction. So if the rate constant of the decay of the reaction, the previous reaction, or the previous decay is 1.00 times 10 to the power negative 6 per second. That is the first law, or first order reaction. What is the half-life of the iodine 131 in A, in seconds, B, in hours, and C, in days? So let us solve this problem starting with in seconds. So we know for a first order reaction, the half-life is given by 0.693. Remember that equation, divided by the rate constant. In this case, we have 693 divided by 1.00 times 10 to the power negative 6 per second. So this gives us 0.693 divided by parentheses 1 to the power negative 6. It gives us 693,000 seconds. What about in hours? So we know that 1 hour is equal to 3600 seconds. So that would be our conversion factor. So in seconds, in hours, you are going to have 693,000 seconds times 1 hour divided by 3600 seconds. So 693,000 divided by 3600, which is 192.5 hours. So this is in seconds, this is in hours, this is in days. So we know that 1 day is equal to 24 hours. So that is our conversion factor. Therefore, in days, we are going to have 19.5 hour times 1 day, 24 hours. Which is 8.0. Let me just which is 8.02 days. So the half-life of iodine 131 is 8 days, about 8 days, about 193 hours, and 693,000 seconds. That's how we use half-life equations to make calculations. So check the next video for more problems on reaction kinetics.